All right, we're going to continue our look at data, and I'm specifically working my way through models. So I'm going to look at data that has a logarithmic model. But again, we have to see that from the data. So the data we're looking at here is meat consumption or meat production in kilograms by year. So I'll put the years up top and have some different ways we can approach this. So 2000, 2003, 2005. And the consumption of meat, I'm just going to put a C for consumption. And this is in what? Kilograms. What is it? It's the average amount of meat and meat products in kilograms consumed worldwide. So it is meat consumption, average per person. That's an 8. Crooked on my tablet here, sorry. And again, I'm going to sketch the graph. I plotted the graph on the solution sheet, but I sketched the graph with my independent variable being consumption, and I kept my variable as years. One of the things I found when looking at this data, and I got this data from, I think I can look at the data source here. It was a table of data from functions and modeling text, since that's what we're looking at is how we can model from the data. I noticed that the years weren't even. But what's nice is that graphs like this on the domain that we're looking at, the year is an okay variable. Now, when I plotted this, my consumption, I start here. I come up. And there's a little kind of trill upwards here. But if I look at these numbers, they're rising. But it's not an exponential rate. It's almost linear with probably an outlier in the data here. But there's a tendency here, if I look at this, that there's a 3, 4, and then in not quite 2, not quite 2, not quite 1, and not quite 3 from here. And so there's almost a linear nature to this, and I kind of thinking of it as part of a logarithmic curve, and it's the high rise of a logarithmic curve. Now, visually in the data, I'm not 100% sure that would be the best way to model this. But when choosing a model, there's a couple of different ideas that we can look into. And so the one idea looking here is this logarithmic curves have a quick rise then a flattening. And that's definitely the trend to here. These last two data points, because they come quickly through and have an upward kick to them, I'm looking at this as being my driving model, and this maybe being what would be my good word for it? Outliers. And so if I were going to predict this and look at the models, an exponential curve of meat consumption doesn't match this rise here. And a linear curve would shoot past, and this line here would overtake. So kind of a muted logarithmic seems to match the data. if you look at the solutions that I give you back on the homework, I do debate this in choosing it, but because this initial here is looking logarithmic, and these might be outliers, what I'm hoping to do is really get the logarithmic feel up to this point, which I believe is the 2000 point on it, and treating 2003, 2005 as outliers. And then what I would do is if this was my job and I was looking at this data, I would continue to take data to see if I'm coming up here or if these outliers pull back to this. Most growth models are either going to be logarithmic or exponential. It doesn't fit the exponential. It doesn't fit linear. So logarithmic will work really well because the coefficients in a logarithmic curve can kind of blunt the curving part of it. So that was my choice of using a logarithmic model in this. So our logarithmic model is the consumption as a function of time is going to be some coefficient times, and I'll use the natural log because it's easier to compute. The base doesn't matter on a logarithmic model unless it's clear in the data that there's a particular scaling factor, like when we do pH base 10 because the hydronium atoms work really well. And so I'm going to put in my time variable here, and then the whole graph can be shifted by a b constant. And so there's two variables that we need to define the model. Whatever we're multiplying the logarithmic function by, and however much we're shifting it up above 0. And again, your textbook does a good job of discussing that with a logarithmic model. Now, again, I didn't change the year function in here. If we were to change the year, and I was going for a logarithmic model, we can't have a year 0 because the logarithmic function isn't defined as 0. So we'd make this year 1, which makes 1980 year 11, and this year 21, and this year 26, and 31, and 34, and 36. And I didn't like this kind of shifting over, so I kept the years as my time input, assuming that this would approach 0 at some earlier time. Again, I'm really hoping to extend this part of the curve. Now, you can do the 1, 11, 21. I've seen some people try that variable shifting coming across. Just make sure that if you've shifted the variables, then this axis changed. That's no problem, but you shift back when you're done. But this works well with a calculator. Now, we have two unknowns in our model, so we're going to need two equations. So what I did was I said, okay, I'm going to take the starting year, and I know that in 1970 my consumption is 27.1, so this equals 27.1, and I'm going to have some a coefficient and the natural log of 1970 plus b. And then the other year I picked was 2000. I'm going to write it up above. Again, I picked 2000 because the curved part of that, these two numbers seem to spike above that just a little bit. And so the definite curvature is defined from here to here. That's what I'm focusing on the model, as I'm trying to get some predictive value from my data and kind of figure out what's happening with those outliers. So for 2000, it was 38.4. And so my job is to solve for the coefficients. Well, I have two unknowns, so I need two equations. And the easiest thing we can do is we can subtract these two equations. Because if we subtract them, the b coefficient is going to go away, the constant. constant. And so if I subtract this, I get 38.4 minus 27.1, so that's 11.3. I get a natural log of 2,000 minus a natural log of 1970, and the two b coefficients have pulled about. Now this is where our properties of natural logs come into play. I want to pull the a out front because that's the thing I want to solve for. And then I have these two natural logs inside here, which this is a number that I can solve for. But to make it easier on myself in the calculator, I'm going to use my properties of natural logs and write this as one logarithm, so that I have the ratio of the years. And it's this ratio that really is driving my coefficient, using this as my year model. Again, if I scale my years, this ratio changes, my a coefficient changes, but it should scale with the data. And so now I solve for a, so 11.3 divided by whatever my calculator spits out for this, which is approximately 748 for a. So I'm going to come back up and I'm going to put this a into my 2000 calculation. And I'll solve for b. So solving for b, I will subtract 748 natural log of 2000 equals b. I run this through my calculator, and b is negative. It's approximately 5,647. Negative. So I put my model together, and the meat consumption as a function of time is 748 times the natural log of my time minus 5,647. And so notice, for me, by using the year here, these values are large, and it compensates for the year. If you shift or scale the years, these numbers will come down to match the shifting and scaling. And that has come across. And again, I'd ask that you look in the solution packet. I then took Mathematica and I had it do a nonlinear fit to log data, and it came out pretty close. The computer fit this to negative 5972. And 790.814 natural log of t. And so if I let Mathematica do a fit to the data, that's the answer it gave me. And when I plotted it against the data, it fit really nicely with the one outlier that I saw. And so that lets us predict into the future. And if this were my job and this was the data I would use this model, but I'd pay close attention if we were starting to deviate from the model. There's a chance that we could be looking at a sigmoid type calculation going on, and that we could have been more in this part of a sigmoid, which would give her a logistic model. So these models that we've been learning, we learn them from the idea theoretically of how things should work, and we then use those and see if reality matches it. Well, when we're in the field or working on things, sometimes we have the data and we don't know which model is the best. And so this is how you would fit a logarithmic model, and then you take that model and see if future predictions match.